now that we have put this in context, how is this going to be used? Let's look at a slightly more complex example which will show us one scenario where I cannot just choose t equal to 0 and get away with it. I have dA as the execution time of A, dB is the execution time of C, dC is the execution time of C, and before going forward, let me just write down what would be the constraints that I have right now. Okay. What would this correspond to? I need to have xb greater than or equal to xa plus dA, xc must be greater than or equal to xb plus dB, and xa must be greater than or equal to xc plus dC. Okay. So, I have these three constraints that need to be satisfied. Okay. Is this possible? What is there a problem here, and if so, what is it? Right? How can we show that there is a problem with this setup over here? The simplest way that at least I can think of over here is just add the constraints. No matter what xa, xb, xc are, this is the same on both sides, which means we can basically remove it, and what we end up with is dA plus dB plus dC must be negative for this to work, okay, which is fundamentally a contradiction, because dA, dB, dC are execution times. They are the amount of time taken for a given function to execute, and by definition again that cannot be negative. Okay. So, what it tells us in other words is there is a problem over here. This is an invalid data flow graph. How do we fix this? I can just have one delay element on any one of those edges. Okay. Let us see how this fixes the problem, right. But at least conceptually this is exactly the same as what you would do in the case of a combinational loop in a circuit, right. A combinational loop in a digital circuit is not permitted for synchronous design. You must have at least one register somewhere. Okay. Conceptually this is exactly the same thing, right. And if I write down the equation or the constraints corresponding to this, what I will see is xb greater than xa plus dA, xc greater than or equal to xb plus dB. Now, I have xa must be greater than or equal to xc plus dC minus t, okay, and that t that I have introduced over here has suddenly changed the whole thing. Okay. If I now once again add and I cancel out the xa, xb, xc, what I will get is 0 greater than or equal to dA plus dB plus dC minus t, or in other words t is greater than or equal to dA plus dB plus dC. Okay. What does this mean? One iteration of this data flow graph must be greater than or equal to the time required for executing each of the individual units completely. Okay. So, A has to complete, then B has to complete, then C has to complete, only then one iteration of this data flow graph is completed. Okay. Very natural, very intuitive, right, and fits with what we can sort of understand of these data flow graphs as things stand. Let us take this one step further. What if it was n tokens that we had over here, right? If I write down the equations, do the cancellation, etc., what I will end up with is 0 greater than or equal to dA plus dB plus dC minus n times t. Okay. Or in other words, t must be greater than or equal to dA plus dB plus dC divided by n. Okay. Now, this is a little more interesting, because what it is telling you is physically what I have is A, B, C sitting in a loop. There are n token delays somewhere in that loop, okay, in this case on the edge between C and A. But what it effectively means is that in principle at least the average iteration period that I can achieve for this system is going to be dA plus dB plus dC by n, right. The fact that there are n delays somewhere in that loop means that conceptually you can think of it as n copies of this could somehow be executing at the same time and producing n outputs, okay. How do we do that? How do we actually implement such things in practice? We will get to that later, but right now we are just talking about the physical bare minimum constraint, right. The only real constraint that you can put on this is T must be greater than or equal to dA plus dB plus dC by n. You could also say T greater than or equal to dA plus dB plus dC, but that is too pessimistic. You can actually do better than that. dA plus dB plus dC by n, however, is fundamental. I cannot do better than that. Okay. This is essentially the iteration period bound. Okay. For of course this fairly simple graph that we have over here. Okay. How do we take this forward? How do we extend the concept of iteration period bound beyond a single graph like this, a single loop like this? Let us take another example. Supposing I had this, right, as my data flow graph, what would you estimate is going to be the iteration period bound over here? Now what I need to do is actually look more carefully at it and say, okay, how do I actually come up with the iteration period bound, right? Where did the iteration period bound come from in this previous thing? Because of the fact that there was a cycle in the graph or a loop, okay. So effectively it looks to me as though what I need to do in this more complex graph is identify all the loops, okay. The first question is that possible? And secondly, once I have done that, then how do I actually compute the iteration period bound, okay. So first I am going to assume that it is possible to enumerate all the loops. In this case, what are the loops? One of the loops that I have is this one over here, right, and the second one is this one over here, okay, which basically means that the BC B loop, right. I am just, that is one way of sort of indicating what the loop is. It is go from B to C and then back to B, so that completes the loop, right. This has a constraint saying that T must be greater than or equal to dB plus dC, right, because if I write down the constraints just for that one loop alone, what I will end up with is there is one delay element on that loop, and therefore T must be greater than or equal to dB plus dC as far as that particular loop is concerned. For the other loop, what I have is A to B to C back to A, okay. Over here what I will find is T must be greater than or equal to dA plus dB plus dC divided by 2, okay, because basically you will end up with 2T, dA plus dB plus dC minus 2T must be less than or equal to 0, right. That is the constraint that you will see. If I want to satisfy both of these conditions at the same time, what value of T can I choose? Which one should I choose? The maximum among these two, okay. So in other words, T must be greater than or equal to max of these two values, right. Please keep in mind it is not obvious that that is dB plus dC, or that it is dA plus dB plus dC by 2, because it depends on the actual values which you do not know right now. Okay. So, you actually have to compute both of those and find out which is the maximum, and then say okay, t must be greater than or equal to that maximum value. Okay. So, if I have multiple loops, then great, this is one way of finding out the exact value of t, okay, that I can use. There is just one problem. For those of you who have done a course on algorithms, you would probably know that what we are looking for over here is we need to identify all possible cycles in a general directed graph, okay, and in general the number of possible cycles in a directed graph can be exponential in the number of edges that we have, okay, in the number of vertices that we have, okay. So, if I have n vertices in the graph, right, I can have a maximum of n squared edges, right, I basically choose any two vertices and I can have an edge between them, right, but the number of cycles, in fact I will go one step further and call this a simple cycle. What I mean by a simple cycle is one where no vertex is repeated more than once, right. So, in this case, for example, BCB is a cycle, BCBCB is also in principle a cycle. You know, I have gone through the same things and I have ended up where I started from, but that is of no interest to me because I have basically gone through it more than once. I am visiting the node B more than once. Similarly, B, C, A, B, again go to C and then B is also a cycle, but that is essentially a superset of the fundamental cycles, because ABCA is a fundamental cycle, BCB is a fundamental cycle, BCA, B, again go to C and then come back to B is no longer fundamental, okay. So, even if I restrict myself to just sort of looking at what are the fundamental cycles where I never visit a node more than once, right, in principle it is possible to have an exponential number of cycles in a graph, okay. Now, in the domain of signal processing, the kind of graphs that you are going to encounter are fairly restricted. You do not have arbitrary graphs with all kinds of cycles or all kinds of edges in them, right. So, in practice you will probably find that the number of possible things that you have over here are restricted, and therefore you do not have to worry about this exponential blow up in the number of possible cycles, but that does not help you in general if you want an algorithm to be able to compute this iteration period bound, okay. As an alternative, right, so in other words, if I want to compute the iteration period bound, this is one way of doing it, basically enumerate all the cycles and compute, okay, find out this max among all of the cycles.